In this video, we are going to find complex numbers z such that 3z plus 1 times 4z plus 1 times 6z plus 1 times 12z plus 1 equals 2. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. This might just seem like an ordinary quartic equation, but I'm going to share with you a slightly faster way to handle it. My method is to multiply both sides by 4 on this term, and then multiply by 3 on this term, multiply by 2 on this term, and keeping 12z plus 1 the same. So then for the right side, I have to multiply by 2 times 3 times 4 as well, and that's 24. So that means on the right side, I will have 48, while for the left, for the first term, I will have 12z plus 4. For the second term is 12z plus 3. For the third term is 12z plus 2. And lastly, 12z plus 1. Now the reason that I chose to do this is that if I group the terms in this way, grouping 12z plus 4 and 12z plus 1 together, and 12z plus 3 and 12z plus 2 together, and if we expand, then for the first group, for the yellow group, we have 144z squared plus 4 times 12 plus 1 times 12, and that's 60 z plus 4. That's the yellow group. While for the green group, we have a very similar expression. We have 144z squared plus 3 plus 2 all multiplied by 12, and that's 60 again. But for the constant term, it's 3 times 2, and that's 6. So these two quadratic multiplied together is equal to 48. So that's why I chose to multiply by those constants. That's why I picked them. The 4, 3, and the 2. These are the constants that multiplying into each of the terms will give the coefficient of z to be equal to 12, which is actually the lowest common multiple of 3, 4, and 6. Of course, including 12 as well. So now for these two quadratic, they are very similar. It's just the constant is slightly different. One is 4 and the other is 6. So I'm going to consider something like difference of squares by writing the 4 in the first term as 5 minus 1, while for the 6 in the second term, I write it as 5 plus 1. So you can see that I have a plus and a minus over here, which means I can rewrite the product as 144z squared plus 60z plus 5 all squared minus 1 squared, and that's equal to 48. So that means this perfect square is equal to 49, and that's exactly 7 squared. So that means I can say this quadratic is either equal to 7 or is equal to minus 7. So now we're just solving some quadratic equations. For the first one, we have 72z squared plus 30z minus 1 equals 0, or for the other one, we have 12z squared plus 5z plus 1, which is also equal to 0. So solving, for the first quadratic, we should have real roots because discriminant is 30 squared plus 4 times 72, and that's clearly positive. Whereas for the other case, we will have non-real solutions. So simplifying, we have root 1188, and if you want to simplify, it's actually equal to 36 times 33, and so we have minus 30 plus or minus 6 times root 33 over 144, and we can rewrite the coefficients, and so we have just minus 5 plus or minus root 33 over 24. Whereas for the other part, we have z equals minus 5 plus or minus square root of 25 minus 48, and that's minus 23. So the result is I times root 23 over 24. So these are the non-real solutions, and they are all valid solutions. And so this is our final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.